Okay, Randy, can you see my screen?
Yes, it looks great.
All right, thanks. Thanks for that earlier introductions. You set the bar rather high, but it is my aim to deliver. On a technical note, I had a dropout I lost a signal during Dan's presentation at one point, and I realized I had two browsers open, a Chrome and a Firefox, and each had about 20 tabs. And after I closed them, everything's been working fine. So if you have a dropout, because I'm going to have a lot of loops in here, you might want to check and see how many things you have open. So this is revised teletraining from 15 years ago. Those of you who are younger, teletraining was what we used before we had webinars. As I was going through this last week and revising it, I realized, well, it's actually a good thing to present again. It's been 15 years and there were several things that I even had forgotten or needed to be reminded about. And of course, there's been a lot of turnover in the National Weather Service. And although you may have, if you're younger, you may have seen versions of this or parts of this online, it's probably good to hear it from the horse's mouth, so to speak. So my main goal in all of this is to make you feel more confident or comfortable when using supercell motion in operations, to help you better anticipate, especially at the early stages of thunderstorm development or when thunderstorms may be splitting, so you can answer questions about how these storms are going to move, properly draw your warning polygons, etc. So for example, where is this storm headed? It's a question you want to ask, and maybe you see that it's developing mid-level rotation, maybe it's going to start splitting and it's becoming severe and you want to put a warning out, so it helps with that. It also helps before warning operations, having the storm predictions for SRH and other storm relative wind computations, which can also help with things like storm type, because if you know the supercell motion, you can look at the boundary relative motion and see, is this going to be overtaken such that it may develop into a QLCS and not stay as a supercell mode very long. It can also help with longevity. If you see that the forecast supercell motion is, for example, along a boundary, or it's going to keep it in a large favorable warm sector for a while, you might anticipate longer lived supercells. So in this particular case, which I believe I took just from a week or two ago, if you would have drawn the warning to go east-northeast, both storms would have ended up going out of the box, which makes sense because it's split. And by definition, once a storm becomes a supercell, its motion will change. Commonly we see the right mover turn right, but that doesn't have to be the case, and I will show you a couple examples of that. They can actually speed up or slow down, might not have an appreciable change in direction. And you look at the Hodograph for this particular case, which was at Fort Worth 0Z, which would be down this part of the screen, and this animation is from 2 to 5Z. You see that the motions fit pretty well, and you might wonder about this little kink down on the lower level of the Hodograph. And I've seen a lot of cases where you have left movers persist, even though you have some curvature in the very low levels. The storm could have become elevated, the left mover that is, could have become elevated, or because this is over such a relatively shallow layer, only 3,000 feet or 1 kilometer, it doesn't have the ability to have that a detrimental effect on the left mover. So I'm going to give a little bit of background material, roughly the first third of the presentation, and then I'm going to have a lot of examples. But I think this is important to reiterate. There are two fundamental controls that control all storm motion. One is advection and the other is propagation. And advection is very simple. It's just your mean wind and how's that moving the storm along. The second one is propagation, and that consists of several things. And I have 5 listed here that I will review. And the key to supercells is this updraft-shear propagation component. So when we're talking about advection, we're really looking at horizontal momentum and how is this storm moving with the flow through the atmosphere. You could think of dropping a twig into a stream and watching that flow along, and that gives you a sense of what advection is. However, a thunderstorm isn't a solid object. It's a process. There's air parcels rising into the storm, developing clouds, and then you have parcels leaving the storm or descending. So it's a continual process, but that storm is moving along with some representative mean flow. And that layer and the flow that's advecting it depends on a lot of things. How deep is the storm, obviously? What is your elevation? Are you in the western US where you have a shallower atmosphere? How old is the storm? Early storms or young storms tend to be advected with a shallower layer, whereas older storms actually will be advected with a layer that's much higher in the atmosphere. And so there are other factors that affect that. So this is a simple concept, but it's not always just a simple one layer that you would use. But for supercell motion, fortunately, 0 to 6 kilometers works well for the mean wind in most cases. So now we move on to propagation. And so there's 5 components, but this one component is really what's critical to supercells. And that is you have vertical wind shear in the atmosphere, which creates horizontal vorticity that gets tilted into the storm, as we see from this very familiar graph developed from Comet, but it comes from the seminal work of Morris Wiseman and Joseph Clamp, among others, in the 1980s. And so you get rotation on the flanks of the storm, in this case, the southern storm, which would be the right mover over here, and then on the left flank of the northern storm. And that rotation is so significant, it can produce up to 50% of the total updraft strength. Because it occurs on the flanks of the storms, it can then cause that storm to grow preferentially on that flank, and there henceforth it moves in that direction. And that's really the fundamental thing that makes a supercell a supercell. And so with this diagram over here on the left, if you look at the just a couple of vectors here, we have the surface wind, the 5 kilometer wind, just as an example. There's your shear vector. And so for a right mover, you get rotation that would develop on the southern flank, and it would propagate to the south and to the right of that shear vector. So then when you add the mean wind and that updraft shear propagation component, you get your resultant storm motion. And I'll go over on a later slide on more details of that. So that's what makes a supercell a supercell. When the mean wind is weak, then this becomes more noticeable because you can have storms that might move northeast or southwest or southeast, depending upon how the shear vector is oriented. So it can result in fairly, what would seem like erratic motions because the mean wind isn't having a very strong influence, and it all depends upon this propagation due to the rotating updraft. So there's another kind of propagation that's quite common, and that's storms that propagate along their gust front. I should back up here. So advection is just simply the movement of the storm with the mean flow, whereas propagation results because you have new development in a favorable location with respect to the storm, and that causes the storm to shift into that direction. And so in this particular case, we have a supercell that was moving east, and we see storms developing along the flanking line of that storm. With time, some of those storms merge with that storm, the supercell, and these are called feeder cells because they're not becoming the new storm, they're essentially just feeding it in this particular case. So you have the prior motion and then new motion because of this back building along the gust front, or it could be forward building. In some cases, these storms actually become the new supercell, so they are called daughter cells, and that's a terminology that came out of a lot of the work in the 1980s with and even 70s with some field projects. This type of propagation is least likely with low precipitation supercells because they do not have that much, in terms of precipitation to create a strong cold pool, hence gust front. Here's an example animation of that. We see a supercell that was moving southeast out of Montana into western South Dakota, and you see the gust front out ahead of it. I'll let it play a couple times. Initially, storms developed out ahead of it, and this one became actually the new supercell, and then so that was kind of a daughter cell situation, and then we have new cells that developed on that storm's gust front, which was leading to these cells feeding into it, essentially causing the storm to accelerate. So this is a relatively common occurrence. Another very common occurrence, especially in weak mean wind environments, is this propagation along a boundary layer convergence zone, an old outflow boundary, a warm front, that sort of thing. So it's best shown through this example. So we have a stationary boundary here, could be an outflow boundary. A supercell is moving to the northeast, it crosses the boundary, and after some time, a new cell develops in its wake. You can envision you maybe have a southerly low-level jet. It develops along that boundary. A little bit later, you see that the supercell starts weakening on the northeast side. Maybe it's moving into a more stable environment, and the storm on the southwest side is growing and merging on the southwest side of the storm. So in a sense, what you're doing is you're slowing that storm down right here because of the development on the southwest side. And then later on, the old supercell may actually have moved off or dissipated completely, and you have a new mature cell in pretty much the same location. So you have a much slower motion of the supercell because of this convergence than you did before that supercell reached that boundary. And there are several examples of this in the literature. And in this next example is a rather famous one. It's the Bennington, Kansas tornadic storm in 2013, I believe. And we see initially some multi-cells going, and then a supercell develops. It starts moving northeast, but with time, we see it kind of slows down, and we see cells feeding into the southwest part of the storm. And there's actually a whole line of storms feeding up into that. So you end up initially with a few feeder cells and potentially daughter cells where the storm is essentially anchored in the same spot because it continually has new generation on the southwestern flank. And this is something that the method that we use to predict supercell motion does not account for. And that another type of propagation results from storm mergers. This is just one example where you have two storms that are moving along. Of course, on the last slide, we saw mergers as well, but this is a little bit different here in that you have the two storms actually run into each other, and then typically the stronger storm pre-merger is the one that dictates what happens after that. In this case, it could evolve into a bow echo. So this again is best shown through an animation. We have a supercell that's quasi-stationary, and eventually another one develops behind it, runs into it, and then the storm accelerates. So this is a good example of that acceleration process happening. And note that the storm behind it is in somewhat of a different environment because the lead supercell has modified the surrounding environment, and that's why the storm behind it can actually catch up with it. Related to that, and we've already seen hints of that in the previous animation, is that you can have storms that are affected by orography. We have the Black Hills right here in Rapid City and presents all kinds of examples of this happening where you have storms develop because the flow is moving up the hills, or you have the hills acting as an elevated heat source, so air flows up certain parts of the hills because of that. And another common thing that we have is the flow going around the hills or the mountains, and then you have convergence on the lee side. So again, what happens is you get a favorable convergence zone where storms may remain relatively anchored to that area because of continued new development. And it's not just the Black Hills. I'm sure you all have certain terrain features in your area that may favor these kinds of development from time to time. So again, here is an example. The Black Hills are roughly in this oval that I'm outlining, and we had a storm that was nearly stationary, and I actually reviewed the radar data and counted 16 first echoes or new storms that kept growing on the west side and feeding into this supercell. And then eventually we have a line of storms that comes along and merges with it, and it takes off. All right, so all this leads to the so-called B2K, or the bunkers method, as people have called it. Maybe it's been called other things, I don't know, but I just want to point out that it was built on a fairly large data set of supercells. We had 260 cases. That may be somewhat small by today's standards, but in 2000 it was a pretty good sample, and we split them up half and half. Half of them were used to develop the method, the other half was used to verify it against other methods. But there's some key things to keep in mind here. And this, so using today's parlance from this old Dirty Harry movie, a person's got to know his or her limitations. And so if you're using the bunkers method, it's important to know that it was developed using relatively isolated supercells that were to a large extent propagated in a continuous fashion. So they didn't have those other four methods of along the gust front or through a convergence zone or anything like that. So it assumes only advection and the updraft-shear propagation are important. So if these other things are going on, well, it wasn't developed for those other things. And that's what I think is really important for us as forecasters, as meteorologists, to know when it works well and when you have to account for these other things. So it's really a very simple method that takes into account these 2 points. Another thing that I try to stamp down, because over the years, sometimes it's been applied inappropriately. It was never intended to be used to predict tornado motion. And as we know, tornado motion can be very different from the parent supercell because it's in a shallower layer in terms of where the advection would be going on. And we know tornadoes can occlude and turn left and that sort of thing. Now, I am aware of some research that is underway to actually look at predicting tornado motion, especially for so-called deviant tornadoes, but by itself, this method is not meant for that. And why would a person use it for QLCS motion, for example? If you look at, what does SRH really mean for QLCSs? Because SRH, as we have it delivered in the models, is using the motion of a right-moving supercell, and that really doesn't make a whole lot of sense to me. And that's why I think the TWIP team has it right by looking at the bulk shear vector in the lower atmosphere, for example, 0 to 3 or 0 to 2.5, which we might use out here in higher elevation. That makes a lot more sense. So using this, something that's for a supercell for QLCSs, just really doesn't make sense. So very quickly, and this may be a review, hopefully it is, but I would hope that everybody, if you see a hodograph, you could quickly look and say, okay, here's the mean wind, here's where the right and left moving storm motion should be. Based on statistics, the 0 to 6 mean wind works the best most of the time, and this is not something that we weight by pressure. It's just averaging the components from every 500 meters from the surface to 6. And after that, you draw a shear vector from the surface up to about 6 kilometers. And the key then is you have a line that's orthogonal to that shear vector, at right angles, but passes through the mean wind. And then finally, you get your right and left movers that are, again, 7.5 meters per second away from the mean wind, but it's orthogonal to the shear vector. It might be right of the mean wind some of the times, but it's not all the time. And I have some examples to show you about that later. The thing to note is, though, that there's scatter based on our original data set of 3 to 18 meters per second. So a storm might only move a little bit away from the mean wind, or it might move a lot away from the mean wind. And these, in part, are related to all the other propagation mechanisms that we talk to, be it mergers or orography or propagation along a gust front or propagation due to boundary layer convergence zones. So they really complicate matters. And I've spent a lot of times in the last 20 years trying to fine tune these various parameters up here, and nothing really seems to work better. And I think the answer to that is data are messy. It's very complicated to try to sort out or tease out certain relationships when you have 4 or 5 things going on. But considering how simple this is, it works pretty darn good most of the time. And here's just an easier depiction of it, summarizing it with the colors, but your hodograph, mean wind, right angles to the shear vector, and then right and left of that. All right, so now we're going to be moving on to some examples, but I want to summarize some key points right here. So to me, the most important thing by doing this, or by knowing how to anticipate supercell motion, is you can be proactive in your polygon warnings. So I'll have an example of that. Or if you get a call and somebody says, hey, I see these storms just developed, was this one going to hit us? And if you can try to figure out, okay, is this becoming a supercell? Oh, if it does, it's not going to keep moving east towards Rapid City. It's going to move southeast, and it's going to hit all the campers down by Hart Ranch. So there you go. Another key point is that this is supercell motion is shear relative. It's not mean wind relative. Yeah, a lot of the times storms do move to the right of the mean wind, but there are exceptions to that rule. And if you really want to fully understand it, you'll look at it from a shear perspective. The nice thing about this is you can anticipate slow-moving supercells, these so-called torfers, which are storms that produce concurrent tornadoes and flash floods, left movers, and I've heard in some on social media and other places online of these mysterious southwest moving storms. This can explain all that. Another key thing to remember is that when a storm becomes a supercell, its motion must change. That's just by definition. Once it develops that rotation, it must change because that's 50% of the updraft strength. So if you see a storm moving right or turning right, that really shouldn't be a surprise. But note that it doesn't have to turn right as it becomes a supercell based on how the shear vector is oriented. So these other types of propagation that we talked about are going to result at times in very poor forecasts of supercell motion using the simple method that we've developed. So this is a simple method, and there are these other things that can greatly complicate things. But that's again where I think it's exciting as a forecaster to step in and say, okay, I see this boundary here. I don't think it's going to move as fast as this suggests. It's probably going to likely to remain more stationary, that sort of thing. It's also based only on the kinematics or the wind profile, but you can use the thermodynamics for some mean wind calculations. And if there's time, I have an extra slide if anybody has a question about it. Otherwise, I'll probably skip that. So now I have a lot of examples that we will go through here. The first one is how to calculate supercell motion. I think this is really important because I've seen it be sloppy at times by people just taking a quick cursory look, but sometimes the devil is in the details. So here's a case from eastern Nebraska, northwest of Omaha, where we have a boundary that was moving to the southeast, frontal boundary, and we had storms developing along and ahead of that. And if you look at the Hodograph from Omaha, we see, okay, so the surface to 4 kilometer Hodograph, I believe, is in blue, and then the 4 to 8 is in green. You have the mean wind in red, and the left mover and the right mover predictions marked appropriately there. So let's step forward here, and we see a little while later, we have kind of a messy situation. On the left, this is the 0.5 reflectivity from the Sioux Falls radar, and we see a left mover, and which would be moving to the east, and then a right mover, and then a new cell developing, and I have the velocity couplets highlighted over here just to confirm and to show you, yes, this had clockwise rotation, and this had counterclockwise rotation. Incidentally, cyclonic rotation is the same rotation as the direction that the Earth rotates. That's why in the northern hemisphere, cyclonic is counterclockwise, but in the southern hemisphere, cyclonic is clockwise. And so we have splitting supercells again in this particular case. And as we go forward, I'm tracking that first right moving storm. So we see it moving to the east-southeast. And we see the other cell developing to its west. It's starting to get close to it and merge with it. So this is that boundary layer kind of convergence that's going on. And that left mover quickly moved off the display here. The legend in the lower left shows you the motions for the various supercells and the mean wind based off the RAP model, or maybe it was the RUC model at that time. Yeah, it would have been the RUC. So now we go forward a little bit more in time. We see the first right moving storm, the second right moving storm, and a new cell that's developing. Again, if we look at the velocity, now we move the radar. We're looking at a different radar now from that would be Hastings, I believe, yeah. And so we have, again, cyclonic, counterclockwise rotation with these two storms, very close proximity. If we look at the animation now, we see that that second supercell is moving to the south-southeast. The first one is weakening, and then we have a new storm that's developing just to its southwest. All this is happening very close together. And as we step forward to the third time, we see the first supercell that's almost decayed, the second one that's matured, and it's sandwiched between them this third supercell over to its southwest. And again, there is rotation with both of these particular supercells. They're a supercell because they have a deep, persistent mesocyclone, persistent lasting at least 30 minutes and deep through at least a third, half of the storm depth. And again, if we look at the animation for this, we see it's moving to the southeast. All right, so we were very careful and methodical about looking through this. But what if you just plop up the radar and track this thing? Now we're going to track the system. This is a complete animation of the system. You say, oh, wow, this supercell is moving to the southwest. Well, the individual supercells are moving to the south-southeast, and that's what's important for storm relative helicity. It's what the storm sees, not what the system sees. So in this example, you can see if you were looking at the system motion, you would say that's a rather poor prediction of supercell motion, and it would be, but in this case, the supercells are actually moving south-southeast, but you have multiple supercells developing along the line and merging together. So it's a very complicated scenario. And it's almost akin to this multi-cell evolution from these images from Chuck Doswell. You have cells kind of growing, merging with the storm, and eventually they'll take over. So this is a very subtle but important thing, especially when you're looking at storm relative helicity. What matters is what the supercell is seeing, not the entire system. So here is that Omaha Hodograph again, 3 times, but we have on the left, we have the supercell motion plotted just for the 3 examples that I was tracking, where I was trying to focus on the mesocyclone. In the center panel, we have the system motion, so more of the multi-cell kind of system motion. And then on the right, we see the motion of the left mover, which was fairly well predicted. And keep in mind that moved east off of the boundary, so it didn't get into that zone where all that the boundary layer convergence was happening. So finally, I'll show a satellite perspective of this example. And when you look at it again, at first blush, you see this big cluster develop to the southwest. You might say, hey, whoa, you know, this one big supercell that went trucking along here. Well, it was a multicellular, supercellular type of system, if there is such of a phrase. The devil definitely is in the details with that. So I present this example simply to illustrate that it can be really complicated when you try to separate out these different components of storm motion. All right. Okay, so proactive warnings for left movers can be done. And I share this example because, you know, as a Sioux, if you get a message from Howie Bluestein that, hey, you know, your forecast F did really good for this, that makes you feel good. I mean, you know, you're at least doing one thing right in your training program. So in this particular case, we'll let the animation run through again. We had a right moving storm that was potentially tornadic eventually. A left mover split off of that, and the forecaster put out the warning fairly quickly. You can just start to see that it's going here, and gets the warning out. With time, this storm moves out of the box to the right. But the reason it does that is because it loses its rotation, hence it's going back with the mean flow. And so this was a good positive example. Now, do we hit these with 100%? Certainly not. I mean, there's times where we've been proactive and we'll put a warning out for, say, the left mover, and after like 10, 15 minutes, it just totally dies. That happens. Now, because of that, there's times where I'll recommend to my staff, as storms are just beginning to develop, and this is especially true over the Black Hills where all kinds of weird things can go on, I'll say, just do a 30-minute warning, because, you know, wait and see for the storm to show you its hand, so to speak. You might see that it's going to split. Okay, draw a 30-minute warning, and so that way you don't have these really long polygons and things, you know, go south on you. So if you have really good confidence, if you see, hey, there's really strong evidence of a split and they're both very strong, then go for it. But you might not want to go with a 60-minute warning. A 30 to 45-minute warning could definitely be helpful in that situation. All right, so I talked about the importance of supercell motion being shear relative. So I'm going to show you a contrived example here, but then I'll follow up with that. So here's an actual hodograph, and as before with the mean wind, the left and the right movers predicted. Then I also have the older 20R85 and 30R70 techniques. So they show it storm motion to the right of the mean wind. Okay, yeah. Now, what I'm going to do is I'm going to shift this hodograph to the left. So you see I took the origin and I moved the origin to the right. So now the hodograph is shifted to the left. So the right mover and the left mover relative to the shear using the so-called bunkers method are still the same. They're still the same distance from the hodograph. But now these methods based on the mean wind are very near the mean wind. They've changed. Well, let's take this one step further, and now we move the hodograph almost to the left of the y-axis, and now we see that the 20R85 and 30R70 are to the right of the mean wind, but now they're to the northeast of the mean wind, whereas based on supercell dynamics, you would expect the motion to be down here. So I know what you're saying. You're at your office. You're saying, yeah, Matt, this is a contrived example. This might look neat, but it's not real. Okay, so well, here's a real example. This is from Corpus Christi, where you had easterly surface winds, generally westerly winds aloft, and so your shear vector was aligned from west to east. It goes from the surface to 6, so it's pointing west to east. Your mean wind is very close to 0. So what is to the right of the mean wind in this particular situation? It's really hard to define. So in this case, we see that the supercell, here's the observed motion, actually moved away from the mean wind, but again, to the right of the shear vector. So it's a good example of why the shear relative perspective is so important. And also notice in this Okay, so it's one of these southwest moving supercells that sometimes appear mysterious because people look and say, wow, we only had 20 knots of mid-level winds. How can we get supercells today? But note, you have nearly 40 knots of bulk shear because you have a stronger easterly flow at the surface and westerly flow aloft. So here's another example. This is even more strange, more bizarre, where we had a cyclonic supercell moving to the left of the mean wind. So this is western South Dakota. Here's Rapid City, and you see the Black Hills. And here's the storm of interest. It moved to the northwest, and you can see a little bit of a hint of a convergence zone boundary here in the satellite, and it also had its outflow, and it propagated fairly strongly because of those to the northwest. Here's our hodograph, came from the Merriman, Nebraska profiler back when we had profiler data. I had to average it from 20 to 22Z because of missing data and being a little bit noisy. We also didn't have observed soundings because they were contaminated or too far away. Anyway, we see the mean wind is plotted here with the black box. Here's 30R75. That's where that would say the supercell motion would be. The forecast using the method we developed, again, to the right of the shear vector over here. So yeah, not perfect. Here's the observed motion because of those extra propagation components, but it illustrates that the storm moved to the right of the shear vector, not to the right of the mean wind. And you can get these oddball situations with really, with weaker flow patterns where you might have high pressure aloft to the north, and like a monsoonal flow situation can be one of those. Or if you have deep northerly flow, aloft, but yet moist, unstable atmosphere like we do later in the season, that can happen like a July, August. So hopefully this illustrates to you the importance of looking at supercell motion from the vertical wind shear perspective and not the mean wind. Now, speaking of turning right, though, supercells can turn right. They often do, and sometimes this is gradual. If you're just looking at this is a storm total precip animation, by the way, just so you know, it's not a hail accumulation. This is predating MRMS, but we see that we had a supercell, and just for the sake of time, I'm not showing you the actual reflectivity or the velocity, but supercells developed up here in Nebraska, and then they curved to the south. Eventually becoming south. And you can say, wow, you know, what was going on that it was kept turning right? Well, the environment was not the same everywhere. It actually, the shear profile changed with time such that as you got later on in the life cycle of the supercell, the shear changed, so the supercell motion would be towards the south. Now, so this is an example of a gradual right turn. Let's look at this case. This is one where you can make the call. If I would have been able to get pole everywhere set up, I would have done a few questions, but you can answer this. You can go through this exercise where you're at and see what you come up with. So here's an animation of a storm that was becoming severe. And actually at the last time of this frame, the forecaster had they drew a warning for it because it was, I'm not showing the data aloft, but it was becoming severe. So where would you draw your warnings? Think about that for a moment. I do have the mean wind shown on here, which is, you know, to the east, a little bit to the northeast. So where would you draw your warnings? Well, your answer should be, I haven't given you enough information. You're going to want to see the hodograph and maybe look at some radar data. If we look at the hodograph, we see very strong turning of the shear vectors through the lowest 4 kilometers or so, which would definitely favor a right moving storm. And in fact, if you look at the mean wind, that's all on the positive SRH side of the hodograph. The left mover would have positive SRH through a good portion of the lower part of that storm. So that would definitely be not favorable for that. And then we see the mid-level rotation with the storm down here in this panel on the lower right. So what happened? Well, this storm took a huge right turn, as you can surmise from the previous hodograph on the last slide, and it showed that, the warnings turned out to be pretty good for this. I think we had them going to the east-southeast, and then by the time that warning expired, they had to extend it more to the southwest. The storm took an exceptionally hard turn and just shows that 7.5 meters a second away from the mean wind isn't always the best. Sometimes you get strong shear, very strong supercells, and they'll deviate even farther to the right. So, but the key here, again, this drives home the point, is that as a storm's becoming a supercell, its motion must change. So if you think you can draw your polygon based on the past storm motion for this, but you expect a supercell, you're just dead wrong. It's just not going to work out. So you have to be creative in how you move your dot to get the storm motion that you desire. And it takes a little bit of trial and error to do that. Here's the satellite animation from this event, and we see that there's this north-south instability zone. These are LIs here from -6 to -8, so very, very unstable, a good southerly flow. And it's possible that the storm deviated further to the right just because it was feeding off of this instability zone. There's another interesting thing I noticed as I was reviewing this case that I didn't notice before, and that's this above anvil cirrus plume, which was actually pretty evident on the satellite imagery that we had prior to our GOES 16 and 17. Of course, back then, we didn't know what an above anvil cirrus plume was, at least it didn't have that name at that time. So here's another case we had where we had supercells developing on the far western periphery of our CWA. So here's Rapid City. So it's way out west of us, it's way southeast of Billings, way northeast of Riverton, and all of our offices know, and it's the same story. We get storms between us. We have no velocity data sometimes, especially back in 2003 when we didn't have the super res. And so a person can actually track the storm on satellite. And 2 years ago, we had to rely on satellite and lightning to issue some warnings because our radar actually went down during an event or two, and we definitely did not have velocity data. We were able to use the local TV station's reflectivity data for some things, but that wasn't always timely either. So here's an example where we had to rely on satellite and lightning. And then, so what we could do without the velocity data, you could at least track the storm, compare it to the storm motions. In this case, we had a severe left mover at the edge of our radar, and we could basically give us confidence that we have a left moving supercell out there, and it's likely severe just based on what left moving supercells do, and that's typically produce large hail. All right, so getting back to what mean wind you might want to use. So in a nutshell, if you have elevated storms, it's a good first guess to use 1 to 6 kilometers. So basically chop off the lower kilometer or lower 3,000 feet, whatever units you want to use. Here's a case from Little Rock, and this swath I have circled here was a long track of hail from this left mover. And I don't believe it produced this tornado, but a long track of hail and one wind. And we see the 12Z Little Rock sounding, the 18Z had a fairly deep, stable layer, but then a lot of mucape above that. And if you look at the 12Z Hodograph from Little Rock, and you look at that and you say, well, gee, how could you get a left mover to survive in that kind of environment with a strong helicity that would favor a right mover and a strong turning of the shear vectors? Well, it's really not ingesting this lowest kilometer. So if you redraw the Hodograph, you get something that looks like a straight Hodograph, which would favor splitting storms, which we saw in this particular case, especially once the storm got north of the boundary and they were developing right near the boundary. So here's an animation. This kind of dates me. This is using NIDS and data from, I think it was Dolores Kiesling at Comet. She was a great provider of radar data for me before we had GR analysts and all the fancy stuff we do now. But you can see that left mover racing off to the north east in here. And it's quite, well, I should say, it's not uncommon to see these left movers blast north of a boundary, dumping a lot of hail in fairly stable, maybe even foggy, low-level environments, but you've got a lot of mucape, and the effective shear is such that it favors that left mover. The same concept as far as changing your mean wind depth applies for low-top supercells as well. And in general, low-topped 0 to 4, maybe 0 to 5 mean wind would be a good first guess. Here's an example of a monsoonal situation where you had right moving supercells going west and left moving supercells moving toward the south. It looks really odd. How could you get that? When you look at the Hodograph here on the right and you say, that's really odd, but I'm gonna step out of my presentation mode, oops. And if I take this Hodograph and I rotate it 135 degrees, and look at it that way, you say, oh, wow, yeah, that looks like a pretty typical Great Plains Hodograph, strong low-level turning of the wind, maybe weaker flow here in the mid-levels, but yeah, right mover moving down here to the southeast, left mover moving to the northeast. Oh, yeah, that makes sense. But it's just a very atypical flow situation that you have. All right, so now we're going to get to a very interesting case that was brought to my attention by Randy Bowers, and actually I noted it was actually tweeted about, got quite a bit of social media attention. So what is going on here? First of all, I just want to point out on the right image, I have the centroids plotted every 15 minutes of this supercell, which was a cyclonic, right-moving supercell for its entire life. And so it did go southeast and then north and northeast. So we'll go back to the animation here. And I'm sure many people are aware of this, but I'll narrate it. So we have this multi-cells kind of moving northeast, pulsing. Eventually it develops into a supercell and then takes off to the southeast once it's a supercell. Gets to the Oklahoma border, stops, says, oh, I want to go back to Kansas. And that turned out to be a very bad decision because he got blown away by the QLCS. So what's going on in that situation? Again, it was cyclonic the whole way. So that's definitely a head scratcher, but if you look at the Hodographs for this, that'll explain it. In a nutshell, you had the strengthening low-level jet, which changed the shear profile, and the shear vector rotated clockwise, and that changed the motion. So on these Hodographs, they're every 2 hours from 21Z, 23Z, et cetera, to 3Z. Left mover in this purplish color, and then the brown one is the right mover. So once the storm became a supercell around 23Z, it started moving southeast. Okay, well, a couple hours later, the storm motion was near stationary as this low-level jet picked up and the shear vector changed. And then a little while later, the low-level jet increased some more, so your shear vector is actually aligned probably more north-northwest to south-southeast, and then you have the right mover, which is actually moving to the left of the mean wind, whoops, and to the north. So that explains, how this very odd path to the supercell evolved was because of the low-level jet, and that can dramatically change your shear profile, especially when you have weaker flow in the mid-levels. And this was the day where people were wondering, like, are we going to get supercells? The flow is kind of weak. Well, thank you to the low-level jet, we got this and then some. All right, so here's another case, and I thank George Phillips, the former Sioux at Topeka, for giving me this. We have, I'm tracking a supercell here that came on the screen. It's moving steady along as you would predict. It's right on with the storm motion. Everything's going good. It's had a little hook here. It's produced a tornado or two. And then all of a sudden, it almost looks like it gets a touch smaller, but it maintains itself. And you see this hook and it starts shifting to the left, to the northeast, and you still see an incredible hook on here. And it was prolifically tornadic through this period. So what's going on? Typically when supercells start turning left like that, right, they've lost the rotation. And so they're moving back with the mean wind, but not so in this case. Well, if you look at the time, it's during that early evening transition, as we saw on the last slide, the low-level jet is starting to pick up. I'll let it finish this animation, and then I'll go on to the next slide and show you the Hodographs for this, which I got one of them from the profiler at, profiler and Topeka sounding. So what we see here is at 0Z, I think this is actually the Topeka sounding and not the profiler. We have the low-level jet. We see up to 20 meters per second, but then at 2Z, it's up to nearly 25 meters per second, and at 3Z, it's over 27 meters per second. And so that shear vector shifted a little bit. You see how it's now all of a sudden oriented more to the southeast. So the storm motion went from east-northeast to a little bit more to the northeast to almost due northeast. So in this particular case, if you see, the supercell, it starts turning left, but it's maintaining its hook and it's maintaining supercell characteristics, and it's the time of day when a low-level jet increases, then the alarm bells should be going off. Because look at the low-level shear in this case. You have that critical angle is near 90 degrees, and you have this incredible amount of low-level shear. So typically, when supercells turn right-moving supercells turn left, it means they've lost a rotation and they're dying and they're moving with the mean wind. But this is a good exception to that rule. So you really need to be cognizant and probably be especially alert if you see a supercell turning left in the evening and it's maintaining its rotation. So getting back to that Bennington, Kansas example, that was a really good one of where you had all this propagation due to the boundary layer convergence zone. So I have here on the left the Topeka Hodograph from 0Z, and on the right is a NAR plot North American Regional Reanalysis of supercell motion, and that's shaded, and you see the vectors for that. So it's shaded gray, the vectors, and this is meters per second. So here's Topeka, it shows just above 12 meters a second, which is consistent with the observed hodograph. And then back near Bennington, it's more like 6 to 8 meters per second, which is right in line with the first supercell that lasted about half hour, 45 minutes before it started then becoming nearly stationary because of that boundary layer convergence. I also have on this figure moisture convergence, and it shows the strong convergence to the south and southwest of Bennington. So here's a good example where applying your knowledge of the environment, how the storm was moving along a boundary, and how the motion was reasonably slow, so it could be slowed even more through this boundary layer convergence process. And here's a couple more Hodographs showing these kind of situations where you can get tornadic storms and have slow-moving storms, these so-called torfers, and that's a paper that Chuck and I worked on back in 2016. Decent low-level jet, strong shear, then weaker flow in the mid-levels, and that favors this slower storm motion. This was actually the record hailstorm from Aurora, Nebraska, which that was the motion right here. And then there was this other one called the Dressler supercell that Roger Wakamoto wrote a paper about that was more near stationary, and that was a little bit further south, and that was experiencing a lot more of this boundary layer convergence kind of propagation. All right, so actually just about done. This is my last slide, I believe. I just wanted to point out some recent research on sigtor storm motion, supercell motion. You're probably familiar, or at least I'd assume half of you are, with Matt Parker's paper in Monthly Weather Review from 2014, where he looked at soundings from Vortex 2. And if we look at the blue and the red here, the blue is non-tornadic near inflow, and the red is the tornadic one. And the photographs are very similar, but you see the observed storm motion for the tornadic was further away from the hodograph than for the non-tornadic one. So after that, a couple of years later, I decided, well, let's look at all the cases I have. Of course, mine that we've gathered come from a synoptic environment. They're not from field projects, but they did show that for significant tornado events, the observed motion here, which is this purple diamond under the yellow dot, is a little bit farther to the right. And then when you look at cases where you have a lot of large storm relative helicity, the observed storm motion is farther to the right of what is predicted. Now, it just turns out I'm actually currently looking at some research and paper I'm reviewing, and they're looking at soundings from field projects, and they're showing a 4 to 5 meter per second bias further off of the hodograph, to the right of the hodograph, for tornadic supercells. So that's something that's, I guess, in the works now, and I guess it's not published yet, but what I would say from an operational standpoint, if you see a storm that's moving along and you're comparing it to the predicted motion, but all of a sudden it deviates farther away from the hodograph, it doesn't necessarily take a right turn, it could be, but if it deviates farther from the hodograph, then the alarm bells might want to be going off just a little bit. It's very, again, this is very preliminary. There's nothing that's been published about it, but it's just something to keep an eye on. And it certainly makes sense, because if it deviates farther to the right of the hodograph, it suggests that you have a stronger mesocyclone, stronger or more storm relative helicity, potentially favoring tornado genesis. So this is actually not off the press yet. It's just hot, but it's not off the press. So I have a page here put together with a lot of references. This is just some background material, but if you scroll down when you go to this page, there's a lot of references from the work that we've done over the past 20 years. So if you've been, this is the money slide, this is the last one. If you haven't been paying attention, if you've been in your kitchen baking cookies and trying to watch this at the same time, now's where you actually have to pay attention, because the one thing I want you to take away from this is that you need to have a procedure with radar and or satellite, they can be combined or separate, I don't care, where you have the mean wind, the right moving storm motion, and left moving storm motion plotted on that. That's really fundamental to applying this. And if you don't have that, you're going to be like my friend John from Texas, and where you don't know which way you're going to go. But having this information will be extremely helpful to you. It's not always going to give you the right answer, because there's these other things that are going on in terms of propagation, but it will get you in the ballpark, and then you can use your meteorological skills to adjust as needed. All right. Thanks for your attention, for listening today. I wanted to make sure I got done by lunch, so I apologize if I spoke too rapidly for some of you, but I know it's death to go over into the lunch hour, which it will be here in Central Time shortly. So back to you, Randy.